Hey everyone, it's Dr. Garner here. In this lesson we're going to look at nuclear reactions. So nuclear reactions are processes that involve a change to the nucleus of an atom. So in other words, they're processes that might change the number of neutrons or protons that are found within the nucleus, and because of that they may result in a change to the elemental identity of a particular atom. So in other words, an atom might change from being one element to another as the result of one of these nuclear reactions. This is in contrast to a chemical reaction. So chemical reactions are processes that only involve the rearrangement of electrons. So in other words, potentially the forming or breaking of chemical bonds that hold atoms together in particular ways. So chemical reactions are the processes that we learned about in the last lesson that result in the formation of molecules and ionic solids. Whereas during a chemical reaction, it's just the electrons that rearrange. So the identities of the nuclei stay the same. So the nuclei of each atom remains the same. So the identity of each atom stays the same during a chemical reaction. So some isotopes are unstable, and because of this, they spontaneously emit particles and/or energy through a process known as radioactive decay. And you might hear this also referred to as radioactive emission or nuclear decay. All of those terms mean the same thing. So we have an example of this here. Shown on this slide is the example of tritium, or hydrogen-3. So that's just a special name that's given to the isotope of hydrogen that has a mass number of 3. So tritium is an example of an unstable isotope that undergoes radioactive decay. So what happens when tritium decays is that one of the neutrons in the tritium nucleus turns into a proton and an electron. So we have a neutron that converts into a proton and an electron. The electron that's formed during this process gets ejected from the nucleus. So this is the particle that's being emitted during this decay process. Now you'll also notice that because we've formed a new proton, the identity of this element is going to change. We go from having an atomic number of 1 because we have 1 proton to having an atomic number of 2 since we have 2 protons in our product. So since our atomic number is now 2, that makes the identity of this atom helium instead of hydrogen. So we formed helium from hydrogen during this decay process. Now the mass number did stay the same here. We still have a sum of 3 protons and neutrons in both cases. So our mass number is still 3, but the identity of the element has changed since we've gained a new proton here. The other thing to note about nuclear decay is that it results in a loss of energy from the nucleus. So you can see here initially tritium contains more energy, at least as reflected by this axis here, than the product, the helium nucleus. So during the course of the reaction, our hydrogen nucleus loses energy as it's converted into helium. So it loses potential energy that's emitted from the nucleus. So again, we're emitting energy as well during this decay process. This is just one example of one mode of radioactive decay. On this slide, I want to take a look at several other modes of nuclear decay, and we're going to talk about what happens during each process. The first mode that we're going to look at is alpha decay. During alpha decay, a nucleus emits what's known as an alpha particle. And an alpha particle, and you'll see this represented just with this lowercase Greek letter alpha, an alpha particle is just simply a helium-4 nucleus. So in other words, a nucleus that consists of 2 protons and 2 neutrons. So this helium nucleus is emitted from the parent nucleus that's undergoing the decay process. You'll often see this alpha particle written like this in this nuclear symbol notation, showing the symbol for helium, the atomic number for helium, and the mass number of this alpha particle. Again, it's 4 since it contains 2 protons and 2 neutrons. You'll often see written a nuclear reaction equation, so you'll often see these written like reaction equations. So you can do that for each of these decay processes that we're going to show on this slide. For alpha decay, if we're starting with an unstable nucleus, we'll call this our parent nucleus. We could write that using, again, nuclear symbol notation, where X represents the symbol of the element, Z represents the atomic number, or in other words, the number of protons, or the number on the periodic table for that particular element, and A represents the mass number of this isotope, so in other words, the sum of the protons and neutrons that are found in that atom. So that's our starting material here. That's the parent nucleus. That's the one that's undergoing radioactive decay. If this nucleus undergoes alpha decay, one of the products of that process is of course going to be that alpha particle that's emitted from that nucleus. Our other product is going to be a daughter nucleus. So this is the resulting nucleus that comes about as a result of this alpha decay process. And we can predict the identity and the mass number of this particular isotope based on the fact that nuclear reaction equations always must be balanced. So what I mean by that is that the sum of the mass numbers and the sum of the atomic numbers on each side of the reaction equation must be the same. And you can see that that's the case here. If I look at the mass numbers on both sides of the equation, I can see that in both cases they add up to the same value of A, whatever that value might be. So A on this side, and then A minus 4 plus 4. If I sum those together, I also get A on the right side as well. Same thing's true for the atomic numbers. I have a total of Z on the left side, since it's just this one species. On the right side, I have two species, so I can add together their atomic numbers, Z minus 2 plus 2, and again that adds up to a value of Z, whatever that value might be. So we can use this principle to predict what the product of an alpha decay process would be. We can just simply take the mass number of your original isotope and subtract 4 from it, and we can take the atomic number of the original isotope and subtract 2 from that. Since the atomic number is changing, that means that the identity of the element is going to change as well. So once you know what the atomic number is, you can then look at the periodic table to figure out what element this species is now. So that's what this prime symbol next to the symbol is representing. It's indicating that the identity of the element is going to change as a consequence of alpha decay. Alright, so alpha decay is one mode of radioactive decay. Another mode that we're going to see a few times is beta decay. So during beta decay, a nucleus emits what's known as a beta particle. A beta particle is just simply an electron. And you'll sometimes see this referred to as using this lowercase Greek letter beta. You'll also sometimes see this referred to using nuclear symbol notation, in which we use the letter E as our symbol to represent the electron. We give it a mass number of 0, and we give it an atomic number of -1. So we use that as kind of a placeholder for its atomic number. We can do the same thing for beta decay. We can write out a nuclear reaction representing the beta decay process. So beta decay is the process that we saw on that last slide, in which a neutron was transformed into a proton and an electron, and the electron was ejected from the nucleus. So since a neutron is being converted into a proton, we're gaining a new proton as a result of this process. So our atomic number in our daughter nucleus is going to go up by 1. Now, the sum of the protons and neutrons remains the same, just like we saw in that example with tritium on the previous slide. So the mass number of your parent nucleus and your daughter nucleus is going to be the same. So if you're trying to predict the product of a beta decay process, all you need to do is just keep the same mass number and then add 1 to the atomic number and see which element corresponds to that. Alright, so we have another mode of emission as well, known as positron emission. Positron emission is kind of like beta decay, but sort of the reverse of that. In beta decay, we saw that a neutron was converted into a proton and an electron. In positron emission, a proton is converted into a neutron and a positron. This positron is ejected from the nucleus, so that's the particle that's emitted during this nuclear decay process. A positron is the antimatter counterpart to an electron, so you can kind of think of it as being like an electron, but having a positive charge instead of a negative charge. And you'll sometimes see these positrons represented using this abbreviation beta plus, signifying that they're a beta plus particle. So a positron is a beta plus particle. You'll also see this written using nuclear symbol notation, again using an abbreviation of E for electron, 0 for your mass number, and this time a +1 as a placeholder for the atomic number of this particle. You can do the same thing in terms of writing out a balanced nuclear reaction equation as well. So whatever isotope you're starting with, since we're losing a proton, since a proton's being converted into a neutron, our atomic number is going to go down by 1 in our product. And of course we're going to get out that positron particle as well. So since our atomic number is changing, the identity of the element is going to change as well, which is why I wrote this as an X prime, representing that it's a different element than whatever the original element X was. The mass number here didn't change, so the mass number stays the same during positron emission. The last mode of emission that we're going to look at is gamma emission. So during gamma emission, the number of protons and neutrons found in your nucleus remains the same, and the particle that's emitted is a photon of gamma ray light. So we saw in the during last week's lessons that the gamma ray portion of the electromagnetic spectrum represents the highest energy or the highest frequency or the shortest wavelength types of light that exist. So that type of light, that high energy gamma ray photon, is what's being emitted when a nucleus undergoes gamma decay. And you'll see this abbreviated using this lowercase Greek letter gamma. The number of protons and neutrons found in the nucleus remains constant during gamma decay. So the mass number is going to stay the same during gamma decay, and the atomic number will stay the same during gamma decay. So you emit this gamma ray photon, but the number of each type of particle that's found in the nucleus remains the same. So your daughter nucleus would have the same nuclear symbol as your parent nucleus that underwent the decay process. And again, I just want to take a moment to emphasize that when we write out these nuclear reaction equations, the mass numbers and the atomic numbers are always going to be balanced on both sides of the reaction equation. So if I add up all the mass numbers on the left and right sides, they're going to be equal to each other. If I add up the atomic numbers on the left and right sides of the equation, they're going to be equal to one another as well. All right, thank you for watching. We'll stop there for this video.